This is the first video in which we revisit Atwoods machines. And the difference here is that we are assuming now that the pulley has enough friction such that the rope will not slide, but rather the pulley will rotate. The pulley will have a certain mass, it will have a certain radius. So this is slightly more complex than the Atwoods machines problems we've dealt with in the past, where we've assumed that the pulley doesn't have any mass and that the rope slides without friction over the pulley. Unlike Atwoods machines we studied previously, this pulley is neither massless nor frictionless. Thus, it has a non-zero moment of inertia, which affects both the system's kinematics and its energies. Also here, the tension is not equal throughout the rope. If the pulley is a uniform disc, derive the two rope tensions, the pulley's angular acceleration, and the mass's translational acceleration. So we've got a lot going on in this video, and I'm going to probably go a little bit fast, but we'll see how it goes. Here's our system, and a couple of things. First, we want to realize that mg is pulling down here on the left. The tension on the left is pulling up. The tension on the left must be greater than that. Otherwise, this mass wouldn't be rising. Similarly, the tension on the right has to be greater than the tension on the left, which is necessary for this pulley to start rotating clockwise. And finally, 3m multiplied by g downward must be greater than this tension on the right. So that's a key idea that I've put a couple of asterisks by up here at the top. Then we've been told that the disc has a mass m and a radius r, so therefore the moment of inertia of that pulley is 1/2 mr squared. Here is our bridge equation for acceleration, and then we've drawn two free body diagrams, one for each mass, and then I've drawn this representing what happens with the pulley. So we need to use Newton's second law in translation and rotation, as well as this bridge equation. So here we go. Let's do Newton's second law for rotation for the pulley first. And the tension on the right is bigger, so we're going to go tension on the right multiplied by r, that's the torque from the tension on the right, minus the tension on the left times r, that's the torque in the counterclockwise direction. That needs to equal the moment of inertia of this pulley multiplied by alpha. I'm seeing some r's that can cancel here. Alpha, I want to change right now to a divided by r. So let's do that. If I change that to a divided by r, then you can see that this second r cancels as well. If we simplify this equation, that's going to leave us with tr minus tl is equal to 1/2 ma. So that's what we've done with the pulley so far. Now let's use Newton's second law for translation for each of the two masses. So here we go. TL minus mg is equal to that mass m times the acceleration. That's from this free body diagram. Now the free body diagram in roughly the middle of the screen, 3mg minus tr equals that mass, which is 3m, multiplied by the acceleration. And now we have here three equations and three unknowns. The unknowns are TL, TR, and A, and there are our three equations. So now it's just a matter of solving these. So here's what I'm going to do. I'm going to solve this one for TL. TL is equal to MA plus mg. TR is equal to 3mg minus 3ma. Now I'm going to take both of those equations and I'm going to substitute them into this top one here. Let me scoot up this paper a little bit. So let's see if we can do that. TR is 3mg minus 3ma, and then we need to subtract TL, and that needs to equal 1/2 ma. Now, can we simplify this? Over here, I'm seeing 4ma. If I put those on this side, that's going to give us, I'll use a decimal there, 4.5 ma. And over here, I'm seeing 2 mg. The m's cancel. So I'm seeing that the linear acceleration of this is going to be, what is that? What's that fraction? 4/9? 4/9 of g. That's the acceleration. Alpha, let me scoot back up to the top of the screen here. Alpha is just the acceleration divided by r. So if we know what the acceleration is, then we know that we're going to get that for alpha. So far, so good. Now, let's put in these expressions to find TL and TR. Here we go. TL, I'm looking at this equation right here. It's m times a plus mg. M and a is 4/9 g plus mg. What's that going to be? That's 13/9 mg. And let's now put that same expression in for TR. I'm pointing right there, TR. We're trying to go quickly here. TR is 3mg minus 3m multiplied by a, and a is 4/9 of g. So what is that going to simplify to? This is going to be 12/9, and that's going to be 27/9. So that's going to be 15/9, which is 5/3. 5/3 mg. That was a tough one, but that's how you do it.